Now let's see the address translation scheme by taking the number of bits. Okay, right? So let us take, as we have seen previously, logical address size, that is your process size. What is the logical address size? That is your process size is 2 to the power of m. What is mean by that? If you have 16 bytes of process, then how to convert it into 2 to the power of 2 to the power of 4? Okay, so the m value will become 4. The number of bits to represent the process is 4 bits. Okay, that is m equal to 4, and your physical memory size is 32 bits, right? Physical memory size is 32 bits. How to represent 32? It is 2 to the power of 30, sorry, 2 to the power of 5. Okay, so the number of bits to represent a physical memory is 5 bits. Number of bits to represent a physical memory is 5 bits. Okay, then the address generated by CPU will be divided into two parts. First one P, second one D. Okay, so this particular page offset is your size of the page. That how to define the page offset bits? Very simple. What is the size of the page? Page size equals to, what is the page size? 4 bytes. Okay, so total process, this will be your m. Okay, this will be your m. I'll take this one. Total will be your m bits. M bits means 4 bits, correct? M bits to represent the process. Now out of this, how to represent the page size? 4 bytes. Okay, 4 bytes means 2 to the power of 2 bytes. So page offset requires 2 bytes out of 4 bits. 2 bits out of 4 bits. That means what will be the page number? Page number also takes m minus n, that is 4 minus 2. Okay, it will be 2 bits. It also requires 2 bits. So it will be 2 bits. Here page number requires 2 bits and offset is also require 2 bits. To represent offset, we require 2 bits. Good. Right? Now, how to convert this particular logical address to logical address to page number and offset? Okay, logical address to page number and offset. How? Take 9. Okay, so otherwise assume that it has 6. Let's take one more example, simple example, 6. Okay, if you take the logical address value 6, then what is the 4-bit representation of 6? 1, 2, 3, 4. 4-bit representation of 6, 0, 1, 1, 0. This will be our 6, correct? And last two numbers represents the offset value. Last two numbers represents a offset value, that is D. So what is the value of last two numbers? 1, 0, correct? These two values. Then this particular first two, okay, rightmost bits of leftmost bits of 2 bits, that is 0, 1. What is the value of 0, 1? It is 1. So this one will be your page number, correct? This one will be your page number, and this is 2. This one will be your offset. That means the logical address 6 is divided into 2 comma, sorry, 1 comma 2, right? It will be divided into 6 will be 1 comma 2. Okay, page number, and that is page number 1, the offset value, that is 2. That means if you take this one 16 bit, okay, process size is divided into 16 bit. Okay, so these are bytes that I am dividing. So this is 0th byte, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so here I need sixth location, right? I need sixth location. Then this is page 0, page 1, page 2, page 3. 6 is converted to 1 comma 2. Okay, page number 1. I go to page number 1. Okay, and this will become again from the start. How many it has to move? 2 bytes. Okay, so 0th byte, first byte, second byte. Correct? 0th byte, first byte, and second byte. I need to fetch the value inside this particular 6th byte. Okay, let's take one more example called 3. Let's take one more example, sorry, 4. Let's take one more example. 4, logical address generated is 4, so that it will be clear. Okay, so this particular logical address, what is the value? 4. Okay, what is the value? 4. I will take the value 4, logical address value 4, logical address value 4. Then how it will be divided? It will be divided into 0, 1, 0, 0. Right? It is your binary version of 4. It is our binary version of 4. So this particular binary version of 4, we can divide it into page number and offset. Page number and offset. How? Page number is last 2 bytes. Page number is last 2 bytes. Sorry, page number is last 2 bytes. This is most significant 2 bytes, and there are least significant 2 bytes. So these 2 bytes will require offset D, represents D, and this one will represent page number P. Now what is this one? It is 1. So page number 1 and offset 0. Okay, so 4 is divided into 1 comma 0, that is go to first page and go to 0th location, that is this one, first page and 0th location, and that will be your data, and you need to search this particular location. In this particular location you will find the frame number. Okay, you will find the frame number and you go to that particular frame number and you find, again you need to take 0th location of that particular frame number. Okay, right? So this is how we'll convert using binary to, we'll take binary conversion and we'll find page number and frame number. Okay, clear?
Now let's see the problem with paging technique. Okay, so we need two memory access if you want to access a byte in the main memory. Okay, so how it will be done? The CPU will generate the logical address. CPU will generate the logical address, suppose I. Okay, so we need to access this particular ith memory location. So we must first index 2 because it is divided into page number and offset. Now page number is acts as index to page table. So first we must index to page table. How do we go to page table? Because we have a register called page table base register, where it will points the page table in the main memory. Okay. So if you go to page table, then in that particular page table we will find frame number and we'll combine that particular frame number with the offset. We can find the desired memory location. Okay, desired memory location. So we need two accesses, two memory references and two memory accesses. That is, first one to for the page table entry, second one to access the desired byte in the memory. Okay, that means the memory access is actually slowed down by the factor of 2 here. Okay, so if it takes 100 nanoseconds, okay, 100 nanoseconds to access main memory, then we need two memory accesses. That means we need 200 nanoseconds to fetch the desired byte that is asked by this particular CPU. Okay, so we can use something called translation look aside buffer. Translation look aside buffer. So this particular translation look aside buffer will maintain in a memory called cache memory. Okay, so where this particular cache is resided? On the CPU. Okay, inside the CPU we will have a cache memory. We have a cache memory. So it is a translation look aside buffer is actually stored in cache memory. Okay, right. So